In this video uh, on vectors, we'll be proceeding with the multiple vector addition as opposed to the two vectors that we had considered in the previous cases where we had used the uh, parallelogram law as well as the triangle law of vector addition. Here we'll be using the polygon law, polygon law of vector addition. As per this law, you can have multiple vectors in it and we add them up. So let us assume we have these vectors. Now here I have a set of vectors. Let us say this is A and this is B, this is C, and another one may be D, right? We have these set of vectors. Now, as mentioned earlier in the earlier videos that we had done, we can have the same vector. Suppose we have the A vector over here. This A vector can be represented in the similar way with the same magnitude as well as the direction. Let me use another ink for that. Okay, so I have this A vector. Let me take it over here. So this is the A vector. As you can see, I've tried to get to the direction and the magnitude in a similar manner as that in the given figure. Then from this end point of A, I take the other vector, that is B. So I take the B vector over here. I will try to have almost the equal magnitude and direction just to show you. And this is the B vector, right? And then with B vector over there, we'll be now considering the C vector. So the C vector, both in magnitude and direction, again is almost that. As far as the rough diagram is concerned, we can consider that. And then finally the D vector. Now D vector it is directed in some other direction over there. So let me, for your convenience, as of now, I'll be drawing that D vector once again, but as of now I'll be considering another D vector to make it easier for you to understand. Let me take the D vector like this over here. Let this be the D vector. We'll be doing the D vector that is present over there that I have taken initially, but now for your convenience I'm doing it over there like this. So now the D vector, I'm using this D vector instead of this one for a better understanding of this diagram. I'll be using the D vector, that previous D vector as well later on so that you can understand it properly. So this is that D vector that I have considered just now. Now I take the resultant, and as per the polygon law of vector addition, the resultant is now this is a polygon, obviously multi-sided figure, and this is an open polygon. We have a starting point over here, we have an ending point over here. So the resultant is always from the starting point of the first vector to the ending point of this last vector that we have achieved over here. This gives the resultant. Now, in order to prove that this is correct, let us use the triangle law of vector addition. Now, if you see, we have two vectors. Let us assume this A vector and the B vector in the first place. So, as you know that A is terminating at a certain point, let us say this is O, this is small a being the point where it is terminating, small b is the point of termination of the B vector, point C in small letter is the terminating point of the third vector, that is the C vector, while this D is the terminal point of the D vector. So OD that we have over here is representing the resultant R vector. So now we can take, as per the triangle law, the A vector and the B vector taken in the same sense of an open triangle. The closing side of the triangle taken in the opposite sense must give me the resultant of A and B. So OB vector is nothing but the resultant. Let me take it as R1 as the resultant. So R1 is the resultant of A and B, which means I have R1 to be equal to A vector plus B vector. You can refer to triangle law of vector addition if you are unsure about it, just in the previous video that we had made. So R1 is the resultant of the first two vectors, that is A and B. Now R1 is terminating at the point B, from where we have the vector C to be initiating and terminating at the point C. So now we can consider another resultant which is taken right from O to the point C, and that is the R2 vector, which is the resultant of R1 and C vector. So we have OC vector, which is equal to the R2 vector, which is the resultant of R1 plus C vector. It follows the triangle law of vector addition as well. And finally we have OD vector, which is the final resultant of this entire system of vectors that we have over here. So R vector is nothing but equal to R2 vector plus D vector. Now if you consider this equation that I've just boxed, you have R vector and you have the R2 vector over there. What is R2 vector? I write R2 explicitly, that is R1 plus C vector is what I write for R2 that we have just seen over there, plus D vector which stays out, and finally R1. For R1 I use this equation that I had obtained. So we have, for R1 we have A vector plus B vector, and the C vector remains as such, and finally outside we have the D vector. We can do away with the brackets now. We have A vector plus B vector plus C vector plus D vector. That is all the vectors that are available over there. This R is obviously the sum of all the vectors, which obviously gives the resultant. The resultant meaning the output that we get by adding those vectors. Now let me take this as D primed. Had I considered that vector, obviously that's the point C over there, and from that point C I'll be considering the same magnitude and direction. So let me just take it over here. So this is the D vector, D dash vector you can say, and the figure would have looked a bit odd, and that's why I avoided it in the first place. But now, having known this thing that we have obtained just now, I can consider the initial and the final point. Let this be D dash. So OD dash, that entire line will be giving me the resultant in that case. Figure doesn't look that good with that kind of an approach, so that is why, for your better understanding, I considered the D vector as this one rather than that one. So you can assume any set of vectors. This was just to this assumption, this D vector was just to show you that yes, whatever the law states, that is correct, which means that for an open-sided polygon representing all the vectors both in magnitude and direction taken in the same order or sense, I should say, the closing side taken in the opposite sense from the initial point of the first vector to the terminating point of the last vector considered, gives me the resultant of the entire system of vectors, and that is what the polygon law is all about. and obviously it takes the help of vector addition of two vectors. And the formula, this is the general addition formula of vectors, but you obviously know that we are using the triangle law in this case. So the formula for triangle law is what we had obtained previously, that is relating to the magnitude of the vector that we had obtained. So that being equal to for this part that we have a plus b, had we known the angle between a and b, if we know, then a extends along the black line that I've just drawn, and that is the angle. Let us suppose say that is theta between a and b. So we know the resultant r1 that we are getting over here has the magnitude a squared plus b squared plus 2 times of a b cos theta, or 2a dot b, all under root. So that gives me the addition of two vectors. From that we can extend it to the other vectors, like for the second vector that we have obtained, that is r2, as the resultant of r1 and c, we can say r2 has the magnitude of r1 squared plus c squared plus 2r1 r2 r1c cos, let the angle between r1 and c vector be something like theta 2, right? So from that we have cos theta 2, and we can take it under root. This is, let me just make it clear, this is cos theta 2, right? So these are the methods or the approach that you can take in order to add two vectors or even multiple vectors. But there is a much more efficient way to do it. This works in some way or the other, but there's also an alternative way when we get to know about the components that are associated with the addition of vectors. So we'll be discussing a few properties of vectors, and thereafter we'll be moving over to the method of taking the component of vectors, and that is an efficient way of addition of vectors. But these are the basic rules that we must know. Now, coming back to the properties of vectors, some of the useful properties that we can discuss. We have the first as the multiplication of a vector by a real number. By real number. Now, any real number, say n, when multiplied to a vector a, is simply written as n times of the a vector, which means that, suppose I have this to be a vector. Now this is just a vector a, and I multiply this a with some value. Let us say we are considering 2a. That means it is equal to 2 times of the a vector. It means if we consider the magnitude that is over there, then that magnitude, let me just make it clear to you, this is the magnitude of a, and I consider double the magnitude in this case, so I take another length which is equal to a. So now I have this as 2a vector, in which the direction remains the same while the magnitude gets doubled. So in general, instead of that double, we have the general formula in on the in the form of n over there. So, and n can be negative as well. In case of real numbers, we have n to be negative, and the negative of a, if I consider n to be equal to -1 in this case. So we have -1 times of a, well, that is simply minus a, is a -1 times of the a vector, or that is simply minus a vector. That means, considering that magnitude, once again I'm drawing those dashed lines in the downward direction to just give you a hint of the length of the vector, so that you can know about the magnitude. So the magnitude is the same, while the direction in this case is just reversed. Had I taken -2 times of a, again I would have got this length that is over there, just taken in the opposite direction, that is like this, right? So that is not the length, of course, that is the representation of direction in that case. So this gives me the value minus a vector, which is obviously the negative vector as we had studied previously. Then again, if it's the same thing as considering the multiplication of a vector by a scalar. So if I am to multiply the vector, so if I am to multiply the vector with a scalar, it is the same thing, that I have the value, uh, say any value that I take, as in case of n that I've taken over there, that is obviously a number, and here the number can be a scalar, any scalar quantity that I take. So I can consider this example as well. So it is the same thing of multiplying the vector with a scalar, which does not change its direction. Obviously the negative part of it will take it in the opposite sense, but the just a positive number being multiplied to it will just increase it in those multitudes. Now the third uh, property that I can consider is the vector addition obeying the commutative law. So we have the commutative law in this case, which says that the resultant vector remains the same in whatever order we add those two vectors. So if I have the r vector, that is the resultant of, say, two addition of two vectors, that is a vector plus b vector, then I also have the same result for b vector added to a vector. Obviously that's quite clear, because in terms of magnitude, if you see, if you use let us say the parallelogram law of vector addition, I have this a vector over here, b vector over here, then I have this it's actually giving me the same diagonal every time, because the vectors obviously do not change their direction and magnitude. So anywhere at any point, whether you take the second vector as the first or the first vector as the second, that doesn't really matter, because the vectors hold their magnitude as well as direction, and so their addition will always give the same resultant in each case. And now the that's for the commutative law, and now we have the associative law. So the associative law of vector addition, or obeying the associative law in vector addition, is that it says that the resultant of the vectors remains the same in whatever grouping they may be added. So as far as that polygon law that we just came across a few minutes uh, previously, we have the a and the b vector, and there they must be having some resultant. That resultant when added to C gives a final resultant. In that case, that figure that we considered in the previous page, we had the vector as the R2 vector, if you observe that. So in considering that, we can also write this as A vector plus B plus C vector. This is all about the associative law, which states now B and C vector will be having a certain magnitude, right? And with that magnitude, with that vector that we are getting for B plus C, when that added to A, that will give the same resultant for this entire thing in both the cases, right? So it's the associative part of it. Now we can take an example though. You can consider the same example, but because the figure over there was a bit clumsy, so I would like to redraw for your better understanding. So take a fresh page over here. So we have this vector. Let us say I have. Let me take this one. A plus B with like this A. This is the first vector A, and then the next vector is B vector. I'll be using the triangle law of vector addition for terminating a vector. The terminating point of one vector is the initiating point of the other. So in this case, I have the resultant by the closing side taken in the opposite order. So this is just A plus B, right? And if I consider another vector, let us suppose say this is C. So in that case, the resultant over here will be taken will be the can be obtained by using the parallelogram law, because we have the initiating point of A plus B as well as that of C from the same point, so they are co-initial vectors. So I can consider this A plus B goes out of the page over there, um, almost out of the page, and the C vector can be considered over here. It's almost parallel, and this is the resultant that I have, that is R vector, which is equal to R vector is equal to A plus B plus C. Now I take it the other way. I use the C and the B vector. Now you must have the knowledge of the direction of the resultant over there. So I can now consider the C vector somewhere over here, almost the same vector that I'm using with the same magnitude and direction. And now I have the B vector, which was this one. So almost this is the B vector that was considered, right? And because I have taken co-initiating condition, so I can take the resultant in this case by using the parallelogram law of vector addition, where I take the B vector as it is and the C vector over there. This is a B plus C. Right. Now comes the part with A. Now as you can see over there, this one was A, and I can take it from the terminating point of B plus C over there, and I take this as A, almost parallel and of equal magnitude. So this represents now the A vector. And if I consider this is as far as triangle law is concerned, I take the resultant finally along this direction, R vector. Now if you observe this and this that I have obtained, they are parallel and almost equal. You can spare me for the uh, mess that I have done over there, but you can redraw that and can obtain the same magnitude if you draw it to scale, provided you take it in centimeters. Suppose, let us say, 1 centimeter for A, 2 centimeter for B, and have them in fixed directions, with uh, the angles intact, then you will obviously end up with the same resultant. This is just a rough approach to the explanation of the associative property of the vector addition. You can obviously use the scale and uh, the geometrical instruments, protractor and everything, and obtain a valid result, a clear result, rather than the mess that I've done over here. Till next time, the next time obviously we'll be carrying on with the more about vectors, maybe the subtraction part, the relative part, even the multiplication of vectors. uh, Many more to go with that. Till next time, thank you.